Let me put up the chat. All right, so gravity. All right, so this one.
This Indian seems to float in the air. It's a feat which for skeptics simply defies belief.
All right, so this one is one of my favorite mind twisters. You already know the answer, so there's nothing surprising here. The question is, can you levitate mind over matter? And most of you guys will say no, right? And if I were to ask you why, you would say because of gravity. How do you overcome gravity, mind over matter? All right, so most of you guys know that this is not doable. At the same time, you're a little bit open-minded enough to think that it would be awesome if you could, right? It's not like something you considered before, but if somebody were to ask you, hey, is it possible, you would probably say no. All right, and then if somebody were to ask you why, you would say, well, because of gravity. So how do you overcome gravity, mind over matter? There are people who believe that this sort of stuff is possible. I just recounted a number of people. Tom Cruise is one of them. My dad, who happens to be a medical doctor, believes that this sort of stuff is possible. In every single religion, regardless of what your religion is, if you're godly enough and saintly enough, you're expected to be able to levitate. Case in point, Jesus walking on water is an example of levitation. If you grew up with these stories, if you're thinking, you know, you're kind of open-minded enough to the possibility of levitation. All right, and that's how it is. So speaking of levitation,
We don't have him in backstage holding.
We're looking for Special Head. We need him to stage now.
What is going on?
Yeah, sorry for the hold. We're looking for the next contestant. He wandered off backstage.
the one that you guys saw was this guy, Special Head, America's Got Talent. So he does this on TV. So the question is this true levitation? He will say it is. That's what he claims, Special Ed. It also says that he did learn how to levitate in Turkey, the country where I'm from. So is true levitation possible, mind over matter, without resorting to any sort of magic tricks, illusions, technology? Can we really levitate? Once again, there's enough from religious literature. Like I said, Western, Eastern, it makes no difference. In every single religion, they make allowance for people to be able to levitate. Case in point, Tintin, 1959, talking to a Tibetan monk, and then in the middle of a conversation, he starts levitating. And not to mention the stories from the New Testament, the miracles that Jesus performed. And the anecdote that he was walking on water, a form of levitation. Almost makes you want to believe in this sort of stuff. All right, so if levitation were possible, you will see people levitating all over the place, right? On trains, coffee shops.
Wait. Oh my god, oh my god, oh my god, oh my god, oh my god. This can't really be happening. Babe. You're floating. Oh my god.
So the question is human levitation possible? The only argument that you have against it is, how do you overcome gravity? All right? How do you overcome gravity? That's the only argument that you have, is if you really have a good understanding of gravity. What do you think gravity is? All right, let's focus on that one. Is gravity a force? Gravity gives you a weight, right? If you wanted to lose weight, you will lose mass, diet. You could weigh yourself at the surface of the moon. You will weigh 6 times less than whatever it is that you weigh right now. On top of a very tall building, like the top of the Sears Tower, you will definitely weigh less. On an airplane, 30,000 feet up, it's about 2 pounds less. So what is gravity? Is gravity a force? Depends. Newton says, of course it is a force. Einstein will say, no, it's not. So it depends on the definition of a force, right? So what's the definition of a force? Force is what causes acceleration. So the question is, do falling objects accelerate? If the answer to that question is yes, gravity is a force. What do we know? We know that the falling objects do accelerate, and the force always points in the direction of the acceleration, right? So what that means is gravity is a force because the falling objects accelerate. in the direction of the pole, gravitational pull. So the next question is the following objects, did they all accelerate at the same rate, or does the acceleration vary depending upon the weight? We answered that question before, right? What's the answer to that question? The answer to that question is everything falls at the same rate, regardless of their weights. So the next question is why? And your answer in the back of your head is because gravity is going to have the same amount of pull on everything. That as a result, everything falls at the same rate. I got news for you guys. The amount of gravitational pull that you experience becomes your own weight. Does everything weigh the same? Absolutely not. They all fall at the same rate. Why? You don't know the answer, do you? You cannot possibly know the answer because no one knew the answer to this question. This was a mystery until Newton came along. As it so happens, Newton's answer wasn't good enough for Einstein, so he had to come up with his own. About 250 years later, which led us to modern physics, and we're still reaping the benefits of modern physics. Case in point, I'm in Chicago, you're near Houston, and we're doing a live lecture. This would have never been possible if it weren't for Einstein and not liking Newton's answer. Go figure, everything is related. So the following objects accelerate if gravity is a force. Force causes acceleration. So the following objects accelerate, and the acceleration is what a force does. So that means that the gravity is a force. Does gravity extend all the way out to the moon? While something does, all the way from the center of the Earth. If it didn't, what would have happened? Moon would have gone in a straight line at a constant speed, right? Moon would have gone in a straight line at a constant speed. Instead, what the moon is doing is it's orbiting the Earth, which implies that its moon is accelerating towards the center of the circle. If there's acceleration, there's force causing the acceleration directed towards the center of the circle. So the only thing we established so far is apple falls because of a force originating from the center of the Earth itself. And there's also a force extending from the center of the Earth itself all the way out to the moon, all the way out to the moon. So the question is, are they the same forces? So the only thing we established so far is apple falls under the influence of a force because it accelerates. That's what a force does. It accelerates at a constant rate. So regardless of the masses, everything is going to fall at the same rate. Everything is going to fall at the same rate. We also established that we can trace the force out to its source, which means that you can trace it all the way to the center of the Earth. We can also establish that there's a force extending all the way out to the moon from the center of the Earth. As a result, the moon is accelerating towards the center of the circle. And we also established that the force causing the acceleration is in the same direction. So the question is it the same force that pulls the apple down? Extends all the way out to the moon. Is that the same force extending all the way out to the moon? Is that the same force that pulls the apple down? The reason that's a good question is because if it is the same force, if it's the force of gravity extending all the way out to the moon, why then the moon is not falling? Apple is, but why is it that the moon is not falling? Why doesn't the moon also fall? If gravity extends all the way out to the moon, gravity has a pull on it, right? The amount of gravitational pull that you experience becomes your own weight. So what is a weight? It's the pull of gravity. Pull of gravity is your weight. If gravity has a pull on the moon, you cannot be weightless in space. Got it? Yet these astronauts up here weightless in space. So how's that? Because if Newton is correct, just about the only place in the universe you should become weightless is in deep space. What does it mean? Which means that you have to be like a billion light years away from the nearest planet or a star for you to be almost weightless, nearly weightless, not 100% weightless, nearly weightless. If Newton is correct, there's no place in the universe where you will become weightless, truly weightless. That's what it means. So, given the fact that the astronauts appear weightless, given the fact that the moon is not falling, is it gravity that extends all the way out to the moon, or is this some kind of a different sort of force?
Lights, please.
All right, so one of the things that establishes
The law of gravitation was first formulated by the English physicist Sir Isaac Newton in 1684.
1684. 350 years ago, Newton came up with a theory, otherwise known as Newton's law of gravity. Newton knew that whatever this force is caused by the masses themselves. So the masses will attract each other through a gravitational force. Force is going to be proportional to the product of the masses, so which means that you will get to multiply the masses. And then this force is going to diminish with distance. R represents the distance between the masses. So further away the masses are, the smaller the force will become. And then he proposed that the force is going to diminish as the square of the distance. This square implies that in the background, this guy was developing calculus. So that's what he came up with. And then what needs to happen is the adjustment constant. I give you the story of this guy trying to attract this woman. She's not interested, so there's no physical attraction. There's no chemistry, blah, blah, blah. So he's going to try to attract her gravitationally using the Newton's law of gravity or theory of gravity. So the way to do it is obviously there are two things you can control. You can control your own mass, and you can also control the proximity of the distance to the woman. So potentially he could get up to 300 pounds without getting himself killed. And then while she's standing next to her, if Newton's theory is correct, the amount of gravitational pull that these two should be feeling towards each other should be about 1,400 pounds, 14 to 15. What that means is his attraction towards her is going to be about 4.5 times his own body weight. Her attraction towards him is going to be about 14 times her own body weight. She's more attracted to him than he is to her. That's what it means. Well, we know from real life that you don't feel that kind of attraction towards anything. We don't feel that kind of gravitational attraction towards anything. If Newton were correct, smaller objects would have been attracted to us, and we would have been attracted to bigger objects. All right, so we don't feel that degree of gravitational pull towards anything in essence. You wouldn't be attracted to buses, planes, or big buildings. So the amount of gravitational attraction that we feel towards other masses here on Earth is relatively small. The reason why it's relatively small is because of something else in the formula that we excluded, which is capital G. So capital G is the strength of gravity. So the numbers that we came up with, something that needs to be adjusted. So it's adjusted using this constant, which is known as the universal gravitational constant. All right, that's an adjustment constant that's related to the strength of gravity. So universal gravitational constant that you guys are looking at, it's a very small number. It's 6.67 times 10 minus 11, and you got a bunch of units next to it. What that means is you got like 10 zeros before you hit the first number. I mean, this is as close to zero as you could get without hitting zero. All right, so which means that the gravity almost non-existent. All right, so when you make the adjustments to the numbers, any two people standing next to each other will experience a gravitational pull, which is going to be microscopic. So that's the meaning. All right, so this becomes the law of gravity, or the theory of gravity. Newton likes to say law, we call it the theory. All right, so according to the theory, force is generated by the masses. So the multiplication of the masses is going to give you the force, and whatever this force is going to diminish with distance is the square of the distance as measured relative to the center of mass, and capital G represents the strength of gravity. All right, so the next question is falling objects, right? They all fall at the same rate. Falling objects will fall at exactly the same rate in a vacuum, exactly the same rate. Me, 150 pounds of me is going to fall at the same rate as an electron in a vacuum, which happens to be almost weightless. It's got a mass which is 10 to the minus 31 kilograms, which means that you got 30 zeros before you hit the first number. Everything with mass will fall at the same rate. All right, so approximately 10, exactly 9.8 near the surface of the Earth, at the surface of the Earth. This is how fast things fall. So the question is why? Newton came up with an explanation for it. So why is G this number? Why is it that everything falls at the same rate? So place the apple at the surface of the Earth. It's got weight. Weight is caused by the gravitational force. So here's the pull of gravity providing the weight. Left-hand sides are equal, which means that the right-hand sides will be equal to each other. That's what it means. So for G, mass of the object is the apple is going to vanish from both sides. It's going to, as a result, you come up with a formula that looks like that. All right, so what does R represent here? R represents the distance between the Earth and the apple. So the question is, what is R at that zero? What's the distance, right? What's the distance between the apple and the Earth? You're thinking, oh, it's zero. I'm thinking it's not. If you're thinking it's zero, once again, you missed the point. All right, there's a huge gap in your understanding of what's going on, despite the fact that I already mentioned it 3 times. Distance is going to be measured relative to the center of mass, not the edges. So the distance between the apple and the Earth is the distance from the center mass of Earth to the center mass of the apple, which happens to be more or less the size of the Earth. So that's the radius in the Earth. And also, we came up with a mathematical expression that says how fast objects fall will depend on the mass of the planet, and how fast objects will fall depends on the size of the planet, square of the size of the planet. All right, so let's check to see if the theory is correct. All right, so here's the observed value, the measured value. Here's the theoretical value. So that's the theoretical value is the prediction. So this formula makes a prediction. All right, so strength of gravity, mass of the Earth, the radius of the Earth. So let's get a predicted value. If this G is correct, it has to be 9.8. So the experimental value is 9.8. If the theoretical number is 9.8, then the theory is good. Guess what? The theoretical and experimental numbers match. So what does it mean? That means that this formula is correct. This formula captures the reality of what gravity is. That's what it means. So what do we know? What that means is now we can draw conclusions. One conclusion is how fast the objects will fall depends on the mass of the planet. So more massive the planet is, the faster the objects will accelerate. So a planet which is 5 times more massive is going to induce a 5g acceleration. So you will feel 5 times energy. And then you have a strange prediction coming out of this one. So for a given mass, imagine that you find a planet which is exactly the same as it's got the same as the Earth's mass, except it's going to be small. All right. So if this planet is half the size, so you reduce this goes down, this goes up. That's the meaning of the inverse relationship. So size goes down, the gravitational pull goes up. So you find a planet which is 2 times smaller. For a given mass, 2 squared is going to be 4. So it's going to be a 4G environment. 3 times smaller is a 9 GeM arm. All right, 4 times smaller is a 16 GeM arm. 5 times smaller, 5 times smaller is a 25 GeM arm. That's what it means. So you got this weird inverse relationship right now. All right, so measurement is non-point, the prediction is non-point. So you're looking at a prediction. So that means that that formula is correct. So because we know that we have a formula that's correct, now we'll check to see if gravity extends all the way out to the moon. All right, how do we know? How do we do that? Straightforward. If the force responsible for the moon orbiting the Earth is gravity, moon's acceleration should be this value. It's going to be a very small value at this distance. So according to this formula, the acceleration of the moon due to the mass of the Earth at this distance, which is r, 250,000 miles away, should cause an acceleration which is fairly small. And this is 3,000 of a meter per second squared at that distance. All right, so if this force responsible for the orbital motion is gravity, it should cause an acceleration valued near using this formula. The acceleration of the moon should be this value, 0.00273 is the value of the acceleration. And you will get this acceleration only if the force that pulls the apple down, the force that pulls the apple down is the same force that extends all the way out to the moon. So the force pulling the apple down, if it's the same force extending all the way out to the moon, this acceleration should be caused by gravity. That's what it means. All right, so how do we prove that it's gravity that extends all the way out to the moon? The only way you can prove it is, here's a prediction. You have to verify this prediction. Is the acceleration of the moon, measured acceleration of the moon is the same as the predicted acceleration, which means that somebody had to measure this. All right, so Newton lived about 350 years ago, guys. 350 years ago. Just try to wrap your heads around that number. 350 years ago. All right, just wrap your heads around that number. All right, he lived 350 years ago. Do you think they have technology that can measure acceleration, which is this small, for a distance of 250,000 miles? Yes or no? All right, before you say yes or no, let me just tell you what this represents. Remember the acceleration of the train upon hitting it at 60 miles per hour. You're standing in front of the train, you get hit by a train, right? Your acceleration is going to be huge because you're not as massive, large enough to break you apart. Train, on the other hand, is extremely massive. It's extremely massive. It's extremely massive. It's got a mass measured in millions of pounds. Acceleration of the train is going to be unnoticeably small. The acceleration of the train is going to be about this value. Okay, you can barely feel it. It's just a vibration. Do you think you can actually measure an acceleration which is this small for a distance of 250,000 miles, given the fact that while you're on the train, when the train is hitting a person, you can't even feel it? The answer to that question is no. 350 years ago, they didn't have that kind of technology. So Newton is talking to his astronomer buddies, and he said, blah, blah, blah. Just do me a favor, just measure this. Let me know how the numbers turn out. His buddies say, hey, Newton, Cal, we don't have that kind of technology. All right. Instead, they said, we can't really measure a number like that from a distance which is that far out. But instead, we could do something one better or equal to better. What they were able to measure is fascinating. They were able to measure a deviation from a straight line. So the moon, instead of going in a straight line, it falls towards the Earth onto this trajectory that matches the curvature of the surface of the Earth. So there's a deviation from a straight line, which happens to be 1/27 inch per second. So moon deviates from a straight line, a distance of 1/27 inch per second. They say, this is the only thing that we could give you. This is the only thing that we're able to measure. Do with it what you like. There's a bit of a confusion. The confusion is Newton wants them to measure this. This is the only thing that they were able to measure at the time. So next question is it possible to come up with a mathematical model which is going to house the acceleration due to gravity and be able to make a prediction regarding how far the moon is going to fall towards the Earth within 1 single second? Is there any way you could come up with a formula that's going to make a prediction of this deviation that's going to match the observed prediction? Observed number deviation. All right, so which means that Newton knew at the time that he needed a mathematical prediction for this deviation. And then, of course, he turned to the math available at the time, which is algebra, trig, geometry, or whatever. And all of them proved completely useless as expected. So in complete secrecy, he develops a much more powerful mathematical method, which is known as calculus theory. Out of calculus, he comes up with this formula, which you have seen early on in the beginning of this method. This is known as a free fall formula. Now, in this free fall formula, notice that you got G, you got the time, which is right there, and you have the distance followed, which is there. Now, what he needs is a theoretical prediction and something that he could come up with, which is comparable to the observed value. All right. So, predicted value for G is going to get plugged into this formula. All right, let's plug that in. These are the observed values. Now let's come up with the predicted value. So it's going to be 1/2 times G. All right, so here's the predicted value for G. Time is going to be 1 second. So we will plug 1 there. So 1 squared times this. 1 squared is 1 multiplied by this. So this number remains the same, divided by 2. So this is going to give you roughly 1,000th of a meter, which is the same as 1 millimeter, which is the same as 1/20th of an inch. So what does it mean? So it means that their predicted value and the observed values are the same. So here's the proof that the force that extends all the way out to the moon, this force that you're looking at, is gravity, guys. It's gravity. It's not some other magical force. There's no secondary force that comes out of the Earth, extends all the way out to the moon, and that as a result, the astronauts are weightless. There's no such thing. All right. It just so happens the force that pulls the apple is the exact same force that extends all the way out to the moon. This force and this force, they are the same. Just wrap your heads around it. All right. So gravity is the same force that extends all the way out to the moon. The question remains, yeah, but the apple falls, right? Apple falls, literally, it does fall. Why doesn't the moon also fall from the sky, if that's the case? If gravity extends all the way out to the moon, then the astronauts, what the hell? Why is it that they appear weightless? All right, so this 1/20th of an inch deviation from a straight line, predicted deviation, is the proof, because it matches the observational line, that the gravity extends all the way out to the moon. So Newton, around the age of 21 to 22, in order to answer the question, if objects fall because of gravity, why doesn't the moon also fall from the sky? So that was the main question that became his main obsession. In order to solve this problem, comes up with 3 laws of motion that we discussed earlier. Comes up with the law of gravity, the theory of gravity. And in order to solve this problem, also the only way he invents calculus. Right? The guy's only 22 years old, and this is what he accomplished until then. All right, just to give you an idea, I'm going to make an outlandish statement, and I'm hoping that you will take this statement to your own grave. I want you to remember this until you take your last breath. You can take the entirety of the human history, guys. You can divide it into 2 parts. You can do it before Newton and after Newton, and you will see the huge difference that this guy played. Before Newton, day after day, a year after year, century after century, millennia after millennia, life was the same. Nothing has changed. People had meaningless, boring, meaningless lives, and if they were lucky, they would die by the time they were 50. Life was harsh. It was impossible. It was slow. It was boring. It was, for the most part, it was meaningless. And after Newton, look what happened. We do all sciences exactly the way this guy had done his physics. Applied science becomes engineering and technology. Look where we are within the past 350 years. All right. Human lifespan increased. And thanks to technology and science and this and that, look how fulfilling our lives are. And the difference is one single individual. You can take the entire Western technology-based, technology and science-based civilization, and you can just trace it back to one single individual, and that individual happens to be this guy. And the physics that we're doing right now is known as Newtonian physics. Classical physics is known as Newtonian physics. All right, so this guy is a major, major, major difference maker in the way the current history shaped.
Of us.
All right, so we still got problems, right? The problem is, well, you know what? If gravity extends all the way out to the moon, what is gravity? It gives you a weight. Can you be weightless in space? The answer to that question should be no. You cannot be weightless in space.
Have only
right?
experienced a tiny slice of time and space. Most of us
But astronauts
have only
in space appear weightless. Even William Shatner last week, it was oh my god, he was weightless. He was really, really, really impressed with it, right? Captain Kirk, original Captain Kirk, it was like, oh, well, man, it was in tears for 3 or 4. Right? You hit space and all of a sudden you're weightless. Are you really? Are you weightless? And a lot of you guys are thinking, no, you're not weightless, but you know the strength of gravity diminishes with distance. You must weigh really, really less than what you are. Yeah, I know. And that's the reason why NASA sometimes is microgravity, right? So as soon as you hit the darkness of space, at that point, boom, outside of the atmosphere, and then boom, everything just diminishes almost down to 0. It's like microgravity. You weigh as much as an atom does, or an electron does. And here's the mystery of it. Even if you weigh as much as an electron does, which is 10 to the minus 31 kilograms, that means you got 30 zeros before you hit the first number, that electron still should fall at the same rate as I do with my 150 pounds of mass. So the way you guys are thinking, once again, is not the right way of thinking. Just too much common sense. And with a lot of the commonsensical answers that you have in your minds, it's still 100% wrong. So what is the explanation if that's the case? Let's check to see how much does a person weigh in space, 180 miles from the surface of the Earth. Let's check to see if it's even 0 or close to 0. All right, so this d represents the distance to the space shuttle plus the radius of the Earth. It's the same exact formula. All right, so here's the radius of the Earth. This is a big number. And d is 180 miles converted to meters. If g is 0, then you're weightless. If g is very close to 0, then it's microgravity. All right, so NASA will say, oh, these astronauts are weightless, which implies that g is 0. And sometimes they make a little bit of a correction and they go, it's not quite weightless. It's like microgravity, which implies that the gravitational pull is going to be 10 to the minus 6 something. All right, that's what it means. Run the numbers. It's not 0. It's nowhere near 0. All right. Holy macaroni. This is nowhere near 0. Here on Earth, it's 10. In space, it's almost 9. All right. And you're thinking, yeah, but it's a big difference, isn't it? And I'm thinking, no, really? How so? Let me give you an idea of the difference between being here on Earth and being in space. So you have an idea. We can calculate this. So you can take someone who weighs 216 pounds here on Earth, and then you can weigh the same person in space. This person is about 200 pounds in space. Being in space, you lose about 15 to 20 pounds, not more than that. You weigh 15 to 20 pounds less. That's what it means. So what that means is this guy who's in space, who originally weighed 215, now weighing about 200 pounds, this guy still weighs 50 pounds more than 19. That's what it means. I don't think it's fair because, hey, he's floating. I can't. And I'd like to be able to float maybe once a week, especially pre-COVID. I used to work about 10 miles from where I live. And, it's Chicago traffic, Monday mornings. My preference was, hey, I could see school from where I was living, just go onto the balcony and let myself up into school and just float to school once a week. And guys, I should be able to do that because I pay my taxes, right? But you can't, because when you try, what happens? You end up falling like a hot bucket of crap. That's what happens. If these people in space, they're floaters. They're able to float. It's not like they're weightless. And while being more than I do, these guys are able to float. So how's that even possible?
I thought there was a weightless room somehow. I knew that astronauts practiced, and I assumed that there was a place to do it. And I learned that that doesn't exist, but that they can simulate weightlessness in an airplane by doing a parabola, which is sort of like a big roller coaster maneuver in the sky. As you're sort of going over this hump, it sort of tosses you, and then the pilot flies the airplane in an arc that basically flies around you as you are free falling. You really can't wait for the next parabola. I don't know if it's a throwback to some embryonic sort of recollection that we have or what, but it's very soothing and exhilarating and a lot of fun, because I never got to do this because I was always involved in every shot. But anytime one of the actors was not in a scene, they didn't go and rest somewhere. They went to the back of the aircraft, and on every parabola they would play Superman because you felt like you were flying. And there were all kinds of zero-G games going on there with frisbees and footballs and stuff that were a lot of fun. But it's an amazing feeling, and always a little bit of a letdown when you finally land and you're walking across the tarmac, and all the usual rules apply. I thought that there was a weightless room.
So Ron Howard is talking about the way they shot the movie Apollo 13. All right, the entire scenes regarding weightlessness was shot in free fall. So these people were experiencing free fall in the form of projectile motion. In projectile motion, there's horizontal speed, but everything is still falling under the influence of gravity. Right? So everything is falling at the same rate. It's exactly the same as finding yourself in a falling elevator. So what happens when you find yourself in a falling elevator? You will feel weightless. That's it. So everything that you see here is just about everything that you can do inside a falling elevator. Everything. I wouldn't recommend it because here they will let you know when they're about to come to a stop. Inside a falling elevator, the safety system is going to kick in rather unexpectedly. So you don't want to be upside down under any circumstances, or else potentially you can snap your neck. All right, so that's pretty much it. In free fall, you will feel weightless. Projectile motion is an example of free fall. This is a special case of free fall. Objects are still falling under the influence of gravity and gravity only, regardless of their horizontal motion. All right, so how does this explain why astronauts appear weightless in space? Explanation came from Newton himself in the book that he wrote 350 years ago, Principia. He had an analogy of firing a cannonball. All right, and you could just keep firing the cannonball and faster and faster and faster and just follow the trajectory. So the analogy goes like this. So imagine modern analogy of what Newton came up with. Imagine that you're at the surface of the moon. You've got a rifle that can actually fire bullets at varying speeds. 3 bullets fired at the same time at 3 different speeds. Notice that they will reach the ground at the same time. So imagine that somehow you can keep firing bullets faster and faster and faster. Now follow the trajectory of the falling bullet, and notice that the faster the bullet goes, the more the trajectory is going to start to match the curvature of the surface of the moon, at a certain given speed, it's going to match it perfectly. All right, so what that means is unless she takes a step sideways, she's going to kick a bullet to the back of her head, because at that speed, when the trajectory of the falling bullet matches the curvature of the surface of the moon, that speed is known as the orbital speed. So which means that this bullet is orbiting around the moon. What kind of motion is that? It's free fall in the form of projectile motion. So when a space shuttle is orbiting the Earth, 180 miles from the surface of the Earth, at a speed of 17,500 miles per hour, trajectory of the motion matches the curvature of the surface of the Earth. So in essence, this person is in free fall, just like this guy inside a falling elevator. The guy inside a falling elevator is going to feel weightless because he and the elevator are falling at the same rate. Likewise, the person inside the space shuttle is going to feel weightless because he and the space shuttle are falling at the same rate towards the Earth in the form of projectile motion. So orbital motion. All right, so the puzzle solved. In essence, the question was, if objects fall because of gravity, because that's what an apple does, why doesn't the moon also fall from the sky? As it so happens, the moon also falls, just like the apple does. It falls in the form of projectile motion. It falls from a straight line onto a trajectory that matches the curvature of the surface of the Earth. It falls from a straight line, a distance of 1/27 inch per second, onto a trajectory that matches the curvature of the surface of the Earth. That's it. The moon also falls. Puzzle solved.
Gravity is working against me, and gravity wants to bring me down. Oh, I'll never know what makes this man with all the love that his heart can stand. Dream of ways to throw it all away. Whoa, whoa. Gravity is working against me, and gravity wants to bring me down. Oh, twice as much ain't twice as good, and can't sustain like one half could. It's one and more. It's gonna send me to.
So levitation, minor or matter. Is it possible?
Lift your spirits with grilled all-white meat chicken, seasoned rice and beans, a traditional slow-simmered sauce, and 3 melted cheeses for a taste like no other. To experience enchilada nirvana, you gotta think outside the bun.
All right, so I have to qualify this. What I consider as levitation, I don't expect to see anything like this, to be honest with you. This is more movie levitation or stage levitation, so I'm not going to expect to see that. And so the thing that I'm going to qualify is jumping up and down on your ass. I don't accept this as levitation either. What I want to see ideally is I want you to be able to go up without pushing up against the ground, go up without flinching a single muscle, maybe hover for about a second. Okay, so it's not a continuous motion. I want you to hang. I want you to go up and stay and then come back down without flinching a muscle. It's just 1 second is what I'm wanting. Not one continuous motion. It's go up, stay, hang, and then come back down. 1 second. All right, if you could do that, I'll say this is real. Okay, that's what I'm expecting. I'm not expecting anything anything similar to what you see in the movies. All right, that's one of the conditions that I have. So, is there anything out there that's going to resemble that sort of levitation, the sort of all right, so the real levitation. What does it even look like? Let's take a look at that. All right, so this guy's a skeptic. All right, so there are two kinds of people. You got the skeptics in the extremes, and then you have the believers in the other extreme. But both of them, two sides of the same coin. Skeptics are, regardless of how much evidence you show them, they're not going to believe it. And they are believers. It doesn't matter how much evidence you show them, still, they're going to be skeptical. Okay, so they're just not going to believe that this sort of stuff is not possible either. Most of us kind of fall in between somewhere. The question is, what is real levitation should look like? Okay, so real levitation is not going to look like what you think it is. If you could just generate a strong enough spiritual uplift, let's call it the holy force, using the vernacular that my dad came up with. If you could just cancel out gravity, you're not going to hover around. That's just a math. Remember, Earth is spinning on its axis. If you could just cancel out gravity, you will keep on moving in a straight line at a constant speed, at the same speed that the Earth is spinning, right? Because you're already moving with the Earth, and you're going to maintain that speed. That's inertia. So, which means that you're going to get projected out into space at 1,000 miles per hour. That's what would happen, literally. All right, you would literally go through the atmosphere within less than 10 to 20 minutes. You would be spacebound. There's no such thing as hovering around. That's the reason why I said, just don't flinch a single muscle. Just go up, hang in there, just for 1 second. That's what I want. Or anything longer than that, you're going to keep moving into space. So you're going to start to gain altitude. If it's true levitation, just go out there. 1 second is all I require. It's not a continuous motion. Hang in there. Just go up, hang in there for 1 single second. All right. So the true levitation would not look like what you think it is. You're not going to be hovering around. So all of a sudden you go, okay, well, if that's the case, you can make a few arguments, because every time you see someone levitating, notice that there's a levitation stick involved. One argument that you need to have a levitation stick to anchor yourself to the ground, or else you will get projected out into space. All right, so that's would be, if it's a prolonged levitation like that, within 10 to 15 minutes. All right, so in every single religion, if you're saintly enough or godly enough, you're expected to be able to levitate. Got it? And if eyewitnesses claim that this is what the real levitation that they saw looked like, I would go, okay, I would be interested in this, because notice that this person is not hovering. This person is gradually gaining altitude. True levitation will look like this. All right, it's not. This doesn't look like the stage levitation. This looks like the real. All right. So the question is it even possible? All right.
Rather than trying to take control of John Hagelin,
So this guy is charting up his body.
in the 70s,
This guy is a physicist who claims that,
expresses no doubt that levitation is possible,
which means that it's possible.
and that
There's
it's
no
made
doubt. All right. So the evidence of it is
becomes as if
these guys are practicing this
leaps
twice a
up
day,
and
every
tends
single
to
day.
dwell by using float and ultimately, according to the literature, fly.
And here's the evidence of levitation. Is this levitation? Now, coincidentally, this looks exactly like the magazine cover, the picture of the levitating yogi that I saw on the magazine cover. And so looking at it, it looked exactly the same. It's very fuzzy, just like that. And I could tell that this person jumped in the picture. So that's not levitation.
By using the mind, you can
This guy just jumped.
overcome classical gravitation.
Okay, so a couple of pushed up against the floor. This is a push. This is not some kind of a spiritual uplift. He literally used his muscles. This is action and reaction force at work. Pushed up against the ground applied the same force back on him. He jumped, and there was no hang time. I said 1 second, just go up and hang. This was one single continuous motion. This is not levitation. All right, it could be that you do it like 1,000 times, and one time, boom, you go up and you hang. All right, so
that hold us down.
then this is not levitation.
Not by miracle,
It's just
but
jumping.
by taking access to deeper gravitational laws, quantum gravitational laws, which take precedence over those macroscopic laws.
And then let's get the entire community involved. Maybe one person goes up and stays there. I could see that they're just going to be pushing up against the ground, so I'm just going to relax my rules. I say just go up and stay there for 1 second, and then I'll go, okay, I see that this could be possible. Just plausibility argument is what I'm looking for. Just go up and stay there. I'm not seeing it. This
Yogi Fly shares this belief that the flyers are escaping gravity. Is this flight, or is it simply hopping?
It may look like
It's hopping. It's pushing up against the ground. It's projectile motion. These guys are hopping exactly the way we would, except these guys are hopping like double amputees. That's the difference. These guys are Special Olympics. There's a bit of a claim that you hang, but there's no hang.
Marshes yogi flying are in between the first and second stage. That means that they'll go up and they'll go forward a bit and then come back down again. And sometimes there's some suspension.
There's absolutely no proof of suspension so far. There's absolutely no proof of suspension. I didn't see it. If there's a suspension, make it 1 second long, I'll say, okay, there's something here. There's absolutely no suspension
in the air.
They claim that this is a step below real levitation. All right, so
the third
so which means that they don't mean this to be a real levitation. This is like, hey, we're just stepping up to
stage is full mastery of flight.
All right, so the full mastery is going to be.
This hardly squares with what yogis are supposed to have been doing for centuries.
So is there any evidence? All right, so this happens to be more of an illusion. All right, so every time you see a levitation stick, you're dealing with the same illusion. Special head, used to be a street performer, Notice that it's exactly the same gimmick. There's something here he's sitting on it. This is on the street. He would do the same thing on the beach. Exact same trick. All right, so there's an illusion of levitation, but it's not. This almost looks like real levitation. It's not either. It's special head. One more time. This is really well done. Execution is beautiful. He's got some kind of a contraption that he's sitting on, which is attached to this bar. And the attachment is going under his sleeve. So obviously he's wearing gloves, so you're not able to see it. This is beautifully executed. One of the metal piece that he's got is under his glove, so every time he hooks it on, you don't hear it. It's a beautiful execution. This was a prank. You knew that this was more of an illusion. He was just pranking a bunch of people. So it's executed like that.
I don't even know how they're going to react.
Tim Hortons levitation is done by this guy. This guy's a stage magician. I have no idea how he had done it, but there's no claim of true levitation. It's pulled it off. He pulled it off beautifully. These two are
I
actors.
just saw her. She was like up in the air, and I was like, "What the hell is going on?" I don't know. I just don't know what happened.
So basically, nobody in Tim Hortons has any idea what we're doing. Okay. So all the customers, everything, no, even the employees. What?
Mais qu'est-ce qui se passe?
Elle flottait de plus en plus haut. Là, elle se met à redescendre. Je comprenais plus rien.
She looked kind of freaked out, but it was awesome.
Babe, can you hear me?
Est-ce que c'est vrai? Est-ce que c'est pas vrai? I'm still like trying to understand, but I just can't.
I've never seen anything like it before. It was cool.
Hallucinant. C'est bon.
So the question is there any evidence of true levitation? Just about everything that we've seen so far is some kind of a magic trick, an illusion, right? The only reason why all of a sudden I have to keep looking is because of this guy, John Hagel. This guy claims that the real levitation is possible. That's what he claims. And the reason why I'm going to take him seriously is because this guy is a physicist and you're not. So the first thing I have to do is just figure out whether or not this guy is a true physicist or claims to be a physicist. And I did my research. It wasn't that difficult to find information about this guy. I ended up going to my favorite top secret source, otherwise known as Wikipedia. A lot of people don't realize that there's such a thing that is unbiased place where you could go and get the latest research on just about anything. And evidently there's a page on this guy. This guy is a PhD in theoretical physics. He's got a PhD in quantum gravitational field theory. So that's his expertise, gravity is. He's got his PhD from Harvard. All right, so this guy is a true physicist. So the question is,
John Hagelin, a physicist
how's he claiming that this sort of stuff is possible?
who joined the movement in the 70s, expresses no doubt that levitation is possible, and that it's made possible through the laws of quantum physics.
So he's saying that through quantum physics, mind over matter, you can change the shape of the space-time continuum.
These laws, he claims, allow mind to take control over matter.
In turn, you should be able to levitate. So the question is there any validity to his claim? Can you do something like that? All right, so I'm just going to ignore this perspective. I'm just going to focus on something that you can relate to, all right, from a physics perspective. Can we make the argument that you can levitate mind over matter? Okay, so we kind of we started off from Newton's theory of gravity, and then let's focus on G. That's the strength of gravity. Excuse me, it's a small number. It's so small that you will have 10 zeros before you get the first number. And then I'm going to compare that small number to a penny in your pocket expressed in terms of a dollar. All right, take a look at the magnitude of the strength of gravity and look at the magnitude of that strength of gravity in terms of a penny expressed in terms of a dollar in your pocket. Notice that this number, the size of this number is smaller than the size of a penny in your pocket. All right, so here's a question for you. If you got less than a penny in your pocket, what do you have? Nothing. All right. So can you overcome a number, which happens to be, can you overcome a number which is going to give the strength of gravity, which is a number which is less than a penny in your pocket? What I'm asking you to do is, can you overcome something which is nothing? Mind over matter. All right. So this is a number which happens to be something which is almost nothing. It's less than a penny in your pocket. Can you do that? Mind over matter. Just because you've never done it before does not mean that it cannot be done. Just because you don't know how to do something does not mean that it's impossible. Most of you guys cannot build an airplane. Just most of you guys can't build a computer. Just because you cannot do it doesn't mean that it cannot be done. All right. So can you overcome something which is this number, which is less than a penny in your pocket? This is something which is almost nothing. Can you do that? Mind over matter. So I'm just going to reduce the question to this. So is it even possible to overcome something which is almost non-existent? Strength of gravity. If the answer to that question is, obviously, if it's doable, then there's got to be an evidence of it, right? So is there any evidence for true levitation, someone who could do it?
Hello.
So the closest thing that I was able to find is this one.
Namaste. Hi, my name is Dan. It's nice to meet you. I've heard so many things about you. I've been traveling all over Nepal on a quest for real magic. And everyone who I've met, everyone who I've seen, everyone I've talked to said to meet you. So it's an honor, so thank you.
Thank you very much, because I have not magic powers.
No, but people have told me that you have special qualities of meditation, that you can do amazing things with your body through meditation.
I'm very sorry. And this meditation is only for myself, not for other people.
Oh, no, I understand. I'd like you to closely guard my secrets. But I was wondering if you'd just be able to talk to me about it. I've come so far away. You know, maybe we can share about what you do.
Of course, we can talk to you.
Okay. So I brought this with me. I'd like to give it to you as a gift. Okay? Look.
Thank you.
Thank you for allowing me into your beautiful home. I would really like to know some more about your techniques.
It's not easy to understand. It's like an ocean. It's very deep.
Right. Well, I understand your hesitation to show me anything, but if I showed you something, might you reconsider?
Yes, of course.
My entire journey and everything I've done to this point comes down to this. I need to impress this man with one of my illusions in the hopes that he will show me what I've come so far to see.
See the moon?
Yes.
I know the Buddha was born under the full moon. I know how important the full moon is in Buddhist culture. If I take my hands and close my fingers around the moon, I can cause it to disappear.
Very nice.
Thank you.
Very fantastic.
Thank you.
Please sit down.
Okay. So, the thing that I hear the most about you, and you can tell me if this is true or not, is that you have power of levitation. And as a magician, this is something that I'm fascinated with.
Your magic is fantastic, but we're not the same Buddhist meditations.
Yes, I understand. I know you don't want to teach me how to do it or tell me any of what you do, but maybe I could just witness it.
You come from very far away. You show me your scale. I don't know what happened, but I will try on time.
Okay, great.
I need you back. If you still close me, then my energy doesn't know. Yes.
Okay. Right now he's saying his mantra. It's the real deal.
How is he doing that? Have you guys seen this? Have you guys seen this?
Wow.
There's wires. I didn't see anything.
This is crazy. Can I approach you?
Yes.
How do you feel?
Fine, thank you.
You okay? Thank you so much. And seeing and talking to so many people just to see you do that. So thank you very, very much. It's been enlightening. I wasn't sure I'd ever find you. You know, my whole journey through your country has been absolutely amazing and truly magical. And I want to thank you for showing me what you do.
Thank you for finding me. And I remember this. Keep your mind open and always continue to learn.
Thank you. Namaste.
That was amazing. Totally worth it. I don't care if it's real, fake, or illusion. I don't even know, but I don't really know how he did it. I can pretty much guarantee that there were no strings, or I didn't see anything underneath, and I didn't see anything above. But he did tell me in the crew to step back. And I think there's a reason for that. I think there was something that he didn't want me to see.
All right, so here's the backstory. The first time I saw this is like 10 years ago. It's 1:03 in the morning. I'm working on research, and this was in the background. And then this is an American magician, stage magician. Heard of this guy before, and this guy evidently has the power of true levitation, so he's looking for him. And this is a documentary, and eventually he finds him, tries to convince him to put on a show for him. Obviously, the guy is not interested. So it takes a bit of a convincing for him to do that. He's got his camera crew, and then the levitation begins. My initial thought is, I'm skeptical, right? So besides, I'm expecting some kind of magic trick. This guy's not a magician. He's not trying to make money. He says this is part of his yogic practice. But at the same time, I'm thinking, oh, he's just going to pull some kind of an illusion. So he doesn't have a levitation stick, so that's not how it is done. So my first thought is, oh, he's pulling a David Blaine. Impressive. Okay, what does that mean? David Blaine angles it just so that you don't see this other foot that he's using to push up against the ground. And then he creates the illusion of levitation. He does a really beautiful job. So I'm thinking there's a contact point underneath. All right, so the cameraman, I think there are two of them. These guys know what to look for because they're working with the state magician. So all of a sudden they realize that there's no contact point underneath. So the next thing is the wires, where the cables and the wires. All right, you should not be, if you're watching a stage magic, you won't be able to see the wires. They're not going to reflect anything. And everything is going to be hidden in the shadows, so you won't be able to see it. So he's looking for the wires, check to see where the wires are. There's nothing there either. And all of a sudden he's puzzled. He doesn't quite know if this is real or if it's just some kind of an illusion. And if it is an illusion, he doesn't know how this guy is doing it. All right. And all of a sudden he's really, really puzzled. So one thing that I want you to notice is the Tintin, the monk in Tintin, this is a Tibetan monk, and this is a Nepali monk. I think the Nepali ones are from Tibet in general. And notice that there's a tradition of levitation in this culture because the artist, the creator of Tintin, used to say that he was basing his stories loosely on his own life experiences. And next thing you know, you got this monk levitating, and then you see a guy who has the same outfit and general look as this guy is also levitating. All right, so this guy's not a magician. He's not trying to make money, and he already claimed that this is part of the yogic practice. And then next thing you know, this guy's levitating. So once again, the question is that true levitation, right? Or is that just an illusion of levitation? Notice that I spent a lot of time talking about this, right? You know, it's a test question. If it's a test question, how do you answer it? Is this true levitation? Or is this an illusion of levitation? The answer to that question is straightforward. Let's check to see if it fits in with the characterizations, the conditions that I set up for true levitation. Is this true levitation, or is this an illusion of levitation? Number one, this guy did exactly what I said he was supposed to do. He did not flinch a muscle. All right, so he just went up without flinching a single muscle. He went up gradually. He hovered around, and then he came back down. Except he did a lot more than what I asked for. I say go up and stay 1 single second. 1 single second. I didn't mean for him to actually hover around for 2 minutes. This guy went up, hovered around quite a long time, and then he came back down. What's wrong with hovering around? Why is it that I said 1 second? There was a reason why I said 1 second. Because if you go up and just stay there, just hang there, suspend it for 1 single second, I'm gonna go, okay, there's something here. I could say, yeah, this is probably true levitation. But if you go up there and that becomes suspended for 2 minutes, that's not true levitation. Why not? Earth is spinning, guys. This person would start to move towards the ceiling fairly fast under the circumstances. You can't just control your elevation like that. It's not possible. It's not true levitation. I don't know what he did. Very impressive. What he did is very impressive. I've seen it done just as well, if not better, by some stage magicians as well as the street magicians. And I have no idea how those people do it either. Except there's no claim that this is true levitation with magicians. So that's an illusion done by a magician.
Have you ever been hypnotized?
No.
Have you ever been hypnotized?
Yes.
Okay, we're going to try this with you. All right, so why don't you step right over here for me? I want you to think about a time in your life where it's just the perfect moment, a moment that you want it to last forever. And I want you to think about that moment. I want you to close your eyes right now for me. Close your eyes, good. I want you to fall back into that place. I want you just to relax and allow yourself to go right back to that place. Fall back into that place. Fall back into that place. Fall back into that place. Just relax yourself. Just relax yourself. Relax your entire body.
Oh my God, that's awesome. That's awesome. That rocks.
Relax yourself. Relax yourself. Relax yourself.
Oh my god, that's so. I don't know how. I do not have muscle control like that. He's totally out of it. Totally out of it.
Oh, girl!
Holy
Wow, I would never do that. That's crazy.
You alright?
That was so freaking cool. You were totally flat out in the air. Nothing in here. And he had his hands over you like this. Air totally smelled out. And it was so amazing. My eyes open or what? No, you were like you were dead or something. It was so cool. Myself? No, nothing. There was nothing under you. I was looking. There was nothing under you at all.
So is that true levitation? You know the answer is no, right? Because what would happen in true levitation? Earth is spinning on its axis, so you would be going in a straight line at a constant speed, which means that you would start to ascend into the sky. And within 10-15 minutes, you would be in space. You would go through the entire atmosphere for the next 10-15 minutes. All right, so it's a magic trick. It's an illusion. I have no idea how he does it. And it doesn't matter because there's no claim that this is true levitation. This guy, Chris Angel, is really good at his craft. He's good at what he does. And he creates the illusion of levitation. Beautifully, beautifully done. All right, so true levitation, is that possible? Reality of it is, let's take a look at the claim. Remember, this is the number that you're supposed to be overcoming. Number, strength of gravity, you got 10 zeros before you hit the first number. All right, a number which is smaller than a penny in your pocket, expressed in terms of a dollar amount. So can you overcome something which is almost nothing, mind over matter? Well, the problem with that is, number one, I'm playing mind tricks with you under the circumstances. It's fast talking. I'm trying to sell you a lemon. I'm trying to sell you a bridge, and I'm expecting for you to buy it. And for the most part, half of you guys buy into things which are completely made up. All these conspiracy theories that you guys believe is exactly the same thing. All right, it's pulled somebody out of somebody's butt. It stinks, yet it sticks if you're not careful. All right, because you guys are so open-minded at times that when you sneeze, your brains kind of fly out of your heads. All right, so when you take this number, which is almost nothing, multiply it with something which is really big, like the mass of the Earth, and then divide by the square of the size of the Earth, which is still fairly sizable, it gives you a number which is almost 10. All right, that becomes the acceleration due to gravity. And when you take this number, which is almost 10, multiply it by your mass, it gives you a weight. In my case, it's 150 pounds. You think I can overcome 150 pounds mind over matter? How does that even happen? Only way I can overcome something like that is by generating or creating an external force, by pushing up against the ground. In turn, the ground applies a force back on me. Only an external force can cause an acceleration. Even if there's such a thing as spiritual uplift and there's no evidence for it, it would still be an internal force that would not cause you to accelerate. Right? It's not possible. Regarding the other guy, the physicist was talking about, mind over matter. You can actually levitate. That's based upon Einstein's theory of gravity. In Einstein's theory, gravity is caused by the curvature of space-time continuum. According to the quantum version of this theory, which is known as the Copenhagen interpretation, which is nothing but philosophy rather than science, you can influence events in your life by willing. And this guy is making the claim that you could also flatten the shape of the space-time continuum. Once again, it's a belief. It's not science. It's philosophy. There's no evidence for it. All right, there's absolutely no evidence for something like that. And compared to everything that you've seen so far, now you know how the trick is done. All right. The first time you saw this was really impressive. And compared to all the tricks that you've seen, including other magicians, including the monk, this doesn't even measure up in terms of quality. He's got a levitation stick, and then he's got some kind of a contraption going over and under his outfit, and it's set up in such a way that there's something that he hooked that he's going to be sitting on, and that's it. And this contraption is obviously attached to something, some kind of a surface underneath. That little rug, you're not able to see it. It's a much, much more advanced version of what he used to do on the street. Well executed. Just a magic trick. That's an illusion. Smoke to cover what he was able to do. He was able to detach the attachments. And then next step is
without. I'm going to take my action out of. You want to float in air, but it is a yes for me.
not look at the way he walks. He's got all these contraptions under this op-ed, and he's gonna have a really hard time walking. He's taking short little steps.
Float in air, but he can barely walk. Wow.
And then he caught on.
That was amazing. Thank you. I didn't try it.